We want to be able to calculate the approximation error in each of these rules, and it turns out that that error depends on the size of the derivative, well actually the absolute size of the derivative. So for the midpoint and trapezoid rule, we're going to define the number k sub 2 to be an overestimate of the second derivative of the function on the interval that we're looking at. And if that's the case, then the absolute error in the trapezoid rule, denoted by absolute e sub t, is k2 b minus a cubed over 12n squared. And the absolute error in the midpoint rule is the same expression, but 24n squared in the denominator. So notice that the error in the midpoint rule is always less than the error in the trapezoid rule for the same value of n. For the Simpson rule, we use k sub 4, which is an overestimate for the absolute value of the fourth derivative of the function on the interval of consideration. And the absolute error in Simpson's rule is that number k4 times b minus a to the fifth over 180n to the fourth. So let's put this to work. Let's say we want to estimate the maximum error here in approximating integral from 1 to 2, 1 over x dx with n equal 10 using a midpoint rule. So midpoint rule here, we need to find that number k2, which is the error bound on the second derivative. So let's go ahead and bring our error formula down here. And we need to find that k sub 2. So what we're going to do is we're going to start taking derivatives. So our f of x is 1 over x, which is x to the negative 1. And so f prime of x is equal to negative x to the negative 2. And f double prime of x, using the power rule again, will be 2x to the negative 3, which is the same as 2 over x cubed. And we want to estimate that on the interval 1, 2. So if you graph 2 divided by x cubed, that's going to be a decreasing function, right? Numerator's fixed, denominator gets bigger on the interval from 1 to 2 as x gets bigger. So that function decreases, goes to infinity at 0. So that's going to look something like this. And so we want to find, this is our f double prime here, which is 2 over x cubed. So we want to find an overestimate for the function values on the interval from 1 to 2. Well, this is a decreasing function, so that number k2, the best estimate, is going to be the function value here at 1. So our k2, because the function's decreasing, is just going to equal 2 over 1 cubed, which equals 2. And notice x is coming from 1 to 2, so 2 over x cubed is always going to be less than or equal to 2. So now we can go ahead and plug in our formula. So our k2 is 2. Now you could use a bigger number than 2, but then that is going to give you a worse estimate of your error. B and a, so b is 2, a is 1, so this will be 2 minus 1. That gets cubed, and we're dividing by 24. Times n is 10 here, so 24 times 10 squared, 2400. So this is 1 times 2, this is 2 over 2400. And we can go ahead and compute that as a decimal. So 8.333 times 10 to the negative 4, so 4 dots, that's 0.0008. So 0.00083 is our maximum error if we're using midpoint rule with 10 subintervals or 10 rectangles. Now, if this function was increasing instead of decreasing, if that function looked like this, then we would use the function value at 2 instead of at 1 for our number k sub 2. And if it was increasing then decreasing, so say that graph looked like this, so the maximum value is somewhere in the middle, we could just overestimate it graphically. So you could graph on your calculator, do a trace, find the function value at that number, and you could estimate graphically if you wanted to.